I posted some hints, and this is about the quiz. I called it a quiz. It's still just a worksheet. I mean, don't get all worried about it. It's still a worksheet.
Just to put a quiz in the front.
Yeah.
It was more important.
Yeah. It's still a worksheet, okay? What's the difference between a take-home quiz and a worksheet?
Not a lot.
Nothing.
Not a lot, except one sounds more important than the
Yes,
other.
we gotta switch it up if things are, no, I don't know. Anyway,
I got a 90 on it.
quiz, question, this is section 6.3. The polar rectangle coordinates, okay. Problem 4A. And I posted some hints, but let's just go over it. Yes.
I was just printing mine out and didn't upload it. Do you need that handout before you go over it?
Oh, it's okay. Do you want to put it, can you take a picture and put it, it's fine. You guys can fix your 4A if you got it wrong. I'm probably going to do a participation grade on it anyway. See, it's a worksheet.
It's a worksheet.
Participation
So if we just did it, we just,
Okay.
if we at least attempted it.
Yeah, attempt every problem.
If you attempted every problem, fine, whatever.
You can still change it. I just want you to learn from it. Okay. So don't
Okay.
panic.
Well, thank you.
You don't want to learn from it? No. Okay. So, thank you for asking, but that's okay. All right, so 4A, we're going to convert -5 minus 6, and that's x comma y. That's from rectangular to polar coordinates. And that's our theta. Okay? So what are we gonna do here is polar coordinates have multiple representations. So we decided, and this was in the notes, we're going to use a positive R. We're going to keep R positive, and we're going to make, and theta will be between 0 and 360. Well, just less than. Or 0 and 2 pi. The smallest, we said the smallest positive angle. That's equal, okay? So that's what we said. Maybe that's too small. See that? Okay. Since we have multiple representations. So our first step is to draw this in the right quadrant. So draw the quadrant, and -5 would be here, -6 would be 1, 2, 3, 4, 5, 6. Okay, this is -5 minus 6. It's in quadrant 3. If we draw a triangle here, a reference triangle, this would be our R, and our theta will be here. We always do standard position angles, so we start with the positive x-axis, and we want it to be positive. So that's the picture. Okay, so the formulas, which you could get from, this length is -6, this length is -5. You can use the Pythagorean theorem, or you could use the formula. You can find R. R is the square root of x squared plus y squared. So R is going to be -5 squared plus -6 squared is square root of 25 plus 36. And that's the square root of 61. So that's the exact value with square roots. That's R. Okay? You can check what square root of 61 is on the calculator. Second square, turn it on. Second square root of 61. This is 7 point, it's approximately, well, I could write several places, but it's about 7.8. Does that make sense for our triangle? It's 5, 6, 7.8. Yeah, R has to be bigger than the size of the right triangle.
And you would want it as the square root of 61?
Yes, the exact answer would be the square root of 61. And then you're going to check with your calculator. Okay, now we need to find theta. Well, we know that, this is our reference angle, theta prime, is this one. It's a positive angle right here. And its tangent is the same as tangent of theta. So the tangent of theta equals opposite over adjacent equals 6/5. So you could do that. Take that. You want to find the angle whose tangent is 6/5, but it has to be in this quadrant. So if you do tangent inverse, you're going to get an angle, I'll call it alpha. Okay. It's not going to be, you can do tangent inverse of 6/5. What's the calculator going to give us when we do tangent inverse? It's going to give us an angle, our alpha, because our alpha is going to be between -pi/2 and pi/2. This is from, because that's what the function in the calculator gives you. In order to have an inverse, it restricted the domain, and these are the only values. But, or I could write it in degree mode, -90. Okay. We should be able to think in both radians and degrees. Okay, so we're going to do tangent inverse. Second, tangent inverse of 6 divided by 5. Oh, guess what I forgot to do? Do we want it in degrees, or do we want it in degrees? I got to check my mode. When I came out with this, I know this is in radians. So mode, it says it wants it in degrees, so we switch it to degrees. If it wanted in radians, that's fine, we leave it in radians, but it said degrees on the problem. Second switch there. So we'll do, so you've got to check your mode. So we get that alpha is 50.2 degrees. This had to go to 1 decimal place on that, right? Okay, but that's not the answer. What angle is that on this picture? See that? You understand? Oh, can you see that? I need to throw this marker away. All right. .2 degrees would put you up here. Yes, we got to add 180 or pi. Since we're in degrees, we're going to add 180. So our theta, we just got to go another 180 degrees to get to our actual, this is a straight line. So theta is going to be 50.2 degrees plus 180. And that is the 230.2 degrees. Okay, so now we got to remember what we're asked to find coordinates. How do we write coordinates as ordered pairs? So let's write the answer down for r theta now. The exact answer for r is the square root of 61. And it said to write theta in degrees, just one decimal place, or did it? Well, we're going to do one decimal place. Okay. If I forget to tell you how many decimal places, just ask. Put in a little note and show me. Okay, so this is the answer, and now we can check. Okay, let's check this on our calculator. So let's check it. So to check it, first off, our mode has to be in degrees. It's already in degrees. But our mode, because, why does the mode have to be in degrees? Because we want that in degrees. Okay? And then we're going to do second. Let's bring the calculator up. It's second matrix, which is angle. Second, the key says matrix on it, but in yellow above it, it says angle. That's why we're picking second angle. You get the angle. And then we're going to go, we want to go from rectangular to polar and find r. And it has us type in -5, -6. Then we'll do it again with rectangular to polar and find theta with -5, -6. Okay, so second angle, rectangular to polar, r. Subscript. Type in -5, -6. And we get 7.8102. So that checks. We got the same thing. Now let's do it again. Second angle, but now we're going to go from rectangular to polar and find theta. Put in -5. You have to put in the -5, -6. Okay, so it gives us -120. It says theta equals -129.8 degrees to one place. Is that the same as 230.2? Well, so obviously our calculator doesn't know we wanted to make it a positive angle. I don't know what the parameters are on this calculator function, but we wanted the smallest positive angle. So look at theta equals minus, this is not theta, not theta. It's, I don't know, what other, gamma or what, I don't know. So, it's this angle, negative 129.8 degrees. So how are you gonna, what's the coterminal angle that's positive to this angle? You take 360 and subtract 129.8, and you're gonna get, so you take theta is 360 minus 129.8, and that gives you the 230.2 degrees. So remember, we have many representations of r theta, and the calculator didn't give us the one we wanted, so we had to change it. We had to add 360 plus 2 pi. We can add 2 pi, we can subtract 2 pi, or we can add 360, subtract 360. So we had to add 360 to that negative. Questions on that? Yes.
Why wouldn't you just, I feel like this is kind of dumb, but where you're trying to find a positive small angle on that line up there, 129 is from here, from 0 to where R is. Why wouldn't you just add 1 in?
Why wouldn't you what?
Oh wait, never mind.
Okay.
I figured it, never mind.
Okay. All right. So we got to remember. You got to remember that we're looking for the smallest positive angle when we're doing these. We're converting from rectangular to polar. There's many representations, and we're going to choose the one where r is positive and theta is between 0 and 360 degrees, or 0 and 2 pi. Okay. Any questions? This is how you use the calculator. The calculator also goes from polar to rectangular. So it will do that. Did you guys want to see that? So I checked number 3. Number 3 was convert r theta, which is negative 3, 7 pi over 6, to rectangular, x comma y. So you're supposed to use the equations x equals r cosine theta, y equals r sine theta. And that's all you have to do. But to check with your calculator, you can check this with your calculator. So you have to use these, you're going to get the same answer. But since 7 pi over 6, you could use the unit circle. I wanted the exact answer. Use your unit circle to find r negative, so x is negative 3 cosine of 7 pi over 6. The unit circle has 7 pi over 6 here, and cosine is square root of 3 over 2 negative. Cosine at this angle is negative square root of 3 over 2. So you're supposed to give me the exact answer there, positive 3 square root of 3 over 2. How do we check this, though? You do the same with sine. You're supposed to use your unit circle and find the exact answers if it's a 30-degree angle or a 45-degree angle, something like that. Okay, but to check it, again, you're gonna put in, here we want the mode, this is in radians, right? So we have to have the mode equals radians. So turn the calculator on and put the mode in radians. Now you press your second, I'm just going to write angle because, you know, it's above that matrix key. Second angle, and you're going to choose polar to rectangular X and polar to rectangular Y. And you actually just type in -3, 7 pi divided by 6. And it gives you the decimal approximation. So, second angle, number 7, we've got it in radians, so -3, comma, 7 second pi, that's over the caret symbol, divided by 6. And we get 2.5981. And I found x to be 3 times the square root of 3. Close the parenthesis and then divided by 2. So it checks. So you're supposed to give me the exact answer and check with your calculator. Okay? And then the other one, you can put that in, it's second angle, polar to rectangular Y. You just have to make sure your mode's in the right mode. 7 second pi divided by 6. And you get 1.5 or 3/2. And that's the correct answer, too. But that one is the exact answer because it didn't have a square root sign in it. Because sine of 7 pi over 6 is 1/2. Negative 1/2. Multiply it by -3, you get 3/2. Any questions? Did that help on this? No?
Well, it helped, but it didn't tell me that I did like the entirety of four wrong.
You did all 4 wrong.
Like I did most of what four right, but I got the answer, put the answers in the wrong way.
How about if I just give you guys, maybe I won't do a participation rate. Let's give you another day on it.
Another day.
Yeah, I want you to get it right.
Okay.
Okay, so...
Like I did everything, and up till the final part of it, till the answer.
Oh, not that one.
Right.
Okay, so I want you guys to fix your work, your quiz, and I will grade it to participation.
Okay.
I'm changing it. I just want to give you, I don't, you know, I'm just giving you one more day. I know we don't have class tomorrow at 9, but that means you can fix that.
Yeah. Put in my answer. It's the wrong
Okay?
way.
So now you have, everybody can fix that. And I don't mind you, I just worked 4 and I worked part of 3. I don't mind you using what I worked. But you got another part of, so. Questions on that? Any other questions?
Nope.
Okay. All right, we're going to continue. Then with vectors. What's your vector, Victor? reference to.
I get it.
Okay. That's airplane.
I watch that every time I'm watching. All the systems that happen on the phone.
Don't call me Shirley. Oh.
It's my favorite.
Okay. So, all right. Vectors. Let me get my answers to this out. Somewhere in here. Okay, section 6.7 is only 2 pages when we get to it. So that's the good news about that. 6.6 is a lot of pages, so let's see. So vectors involve a magnitude and direction. Scalars have a magnitude but no direction. But there's a directed line segment. You have to know some of these terminology. So to show that 2 vectors are equal, you have to show that the magnitudes are equal, and you have to show that, so this is the notation for magnitude, and that they have the same slope is one way. They have to have the same direction, so it should be the slope. So scalar multiplication is multiplying a real number k and a vector v. It is written k, v. Okay, so they boldface the vectors instead of putting arrows over them. But when we're writing, we can't boldface our vectors, so we put arrows over them, or at least half an arrow. Sometimes you'll see it written as k, like that. Put some sort of arrow. I put a whole arrow. So multiplying a vector by a positive number, except 1, changes the magnitude of the vector but not its direction. Multiplying a vector by any negative number reverses the direction. Okay, and if k is a real number and v is a vector, the vector kv is called a scalar multiple. Of the vector v. The vector kv has the same magnitude of the absolute value of k times the magnitude of v. It has the same magnitude of v. Which is, and here's its magnitude. It's the absolute value of k times the magnitude of v. And we just describe this as the absolute value of k times the magnitude of vector v. Okay. The vector kv has a direction that is the same as the vector of v if k is greater than 0. Or a direction that's opposite the direction of v if k is less than 0. The sum of 2 vectors, or 3 vectors, or 4 vectors, however, the sum of 2 vectors would be denoted u plus v, is called the resultant vector. You need to know that term. if we ask for the resultant of some vectors, all you need to do is add them together. So this is very important for you to remember that term. To add these two vectors, position the vectors so the terminal point of U coincides with the initial point of V. Well, this is how you would sketch this. You can do this graphically then. So if this is vector U, and then if this is vector V, then our resultant vector will be right here. In black. That's how you do it graphically. We can also do it by just, if we have the vectors written in terms of I and J, which we'll get to, you can just add the X parts of the vectors together and the Y parts together. So, okay, the difference of two vectors, vector V minus vector U, is defined as, we don't have a fancy name for it, V minus U can be rewritten as V plus the negative vector U. Okay, so if I'm just making up, I'm just making up some, if this is vector U, then the negative of vector U will be here. If this is vector V, then we just add that in our, and this is V minus U. And that's not called the resultant. Unless if you ask for the resultant of V and negative U, then it is. That's subtracting two vectors. But we'll do this with just with numbers. These are the pictures. We have to move the vector V so its terminal point is on the ending point of negative U. All right, now we need to define a unit vector. This is a unit vector. Has a magnitude of 1. And the vector I, it's small I, not capital I, is the unit vector along the positive x-axis. And the vector j, small j, is the unit vector along the positive y-axis. So, if this is a 1 unit, then this is I, this is 1 unit, then this is J. It's 1 unit. It's a unit vector, and it has a magnitude of 1. So we have vectors I and J that are unit vectors along the positive x-axis and positive y-axis. So So if we've got a vector v that goes from 0, 0 to point A, B. So I'm going to sketch this. If this is point A and this is point B, let's make this V. This is vector V. And it can be represented as V equals A times the unit vector I. The AI is this distance, and BJ is this distance. So we can split it up. We can split the vector up if it's not going on the positive x-axis or positive axis or something. We can split it up into its x and y components with vectors I and j. Okay? Does that make sense? The real numbers a and b are called the scalar components. Of vector v, with a being the horizontal component and b is the vertical component. The sum AI plus BJ is called a linear combination. And to find the magnitude of vector V, the magnitude of vector V is just going to be, it's just the distance. The distance from here to here is A. The distance from here to here is B. It's the square root of the distance, Pythagoras theorem. Okay, so we're going to have vectors and they're going to be written this way. So to add vectors, all we have to do is add their components. We haven't got to that yet, but all right. So sketch the vector 3i minus 3j and find its magnitude. Okay, so we want to sketch. So 3i will be 1, 2, 3. So we're going to sketch. Here's 3i. Minus 3j, 1, 2, 3. We got to move it this way. And here's our vector v. V equals 3i minus 3j. Okay, and then we need to find its magnitude. Well, the magnitude, the symbols for that, this means the magnitude of a vector, two straight lines, is of a squared plus b squared. 3 squared plus a negative 3 squared, that's 9 plus 9 is the square root of 18. And of course you have to reduce that. That's the square root of 9 times 2 is 3 square root of 2. So that's the magnitude. Okay, now what if you have a vector that's not at the origin? What if the initial point of the vector is x1, y1, and the terminal point is x2, y2? We're saying that will equal the position vector. A position vector has its initial, a position vector has its initial point at the origin. So we can move this vector v that's originally somewhere up, say it's up here. Say it's up here. That's, I've come on the paper. That's where v is originally on this picture. So we can move that down here. How do we get it down there? Our vector v is going to be x2 minus x1 times I, the vector I, unit vector I, plus y2 minus y1 times j. That this vector v is going to be equal to the vector v, and so we just move it to here. This is pretty drawing, I didn't. So if v is a vector with initial point minus 1, y1, 3, and terminal point x2, y2, 2, 7, write v in terms of I and j. So v is just going to be x2, which is 2, minus x1 times I plus y2, 7, minus y1 is 3 times j. So that's 2 plus 1 is 3i, and 7 minus 3 is 4j. Okay, now, so what we just did here, I don't think 13 and 14 are as important. So these are not as important. Okay, but now we're in your problems on the test and on the final, you're going to be given vectors already in this form. So if you have vectors given in this form and you want to add them together, this is what's important. Very important here. V plus W, vector V plus W is, all you do is add A1 plus A2 times I. Just add their X parts and their Y parts. VI, V1 plus V2, J. And this is called the resultant. So we may not tell you to add the vectors together. We may ask you to find a resultant vector. So you need to know you add them. Okay? And then to subtract them, which doesn't have a special name, it's V minus W. Is you just subtract the component. A1 minus A2. I plus B1 minus B2. J. And then you simplify. That's it. So this is the important, to get to the examples that were on the last page of this. So They look like horribly, horribly long notes, but it's a lot of definitions. I'm trying to tell you what's important here for you to know. So, if you're given two vectors, can you find the resultant? I'm just going to use that word. Vector. Yes. You're just going to take 7 plus 4 and 3 minus 5. You're just going to add those together. It's like it's just like terms. 11i minus 2j. Okay? How are we going to take b minus w? We're going to rewrite it as b plus a negative w. And negative w, remember these are vectors, is negative 4i plus 5i j. Just change the sign. Change the sign. So then that is 7 minus 4 and 3 plus 5. That's 3i plus 8j. Okay? All right, one more thing. If we're going to multiply by a scalar, what happens here is we take a vector multiplied by a scalar. We will multiply each x and y component by that scalar. It equals k times a plus k times b. So that's how we multiply by a scalar. Multiply each component by that scalar. So 8 times vector v will be 8 times 7i plus 8 times 10j. 8 times 7 is 56 plus aj. So if you're multiplying by a scalar before we're adding, we need to do that first. Multiply before we add. All right, multiply by negative 5 times b is negative 5 times 7i plus negative 5 times 10j is negative 35i minus 50j. Any questions? Is this making sense now that we got to this is what you need to know. Okay. All right. The vector whose magnitude is 0 is called the 0 vector and can be written as 0 arrow equals 0 times I plus 0 times j. The unit vector for any non-zero vector v is, you're going to take vector v, and in order to make it 1 unit long, you're going to divide by the magnitude of v. A unit vector has to have a magnitude of 1. So if we take our vector v and divide by its magnitude, we will get a unit vector. So find the unit vector. Now we don't really have room to get the paper. I'm not going to crowd it in there like I did. Find the unit vector in the same direction as v equals 4I minus 3j. Okay, so the unit vector in the same direction as v is going to be v divided by the magnitude of v. So we're going to find the magnitude of v is what? The square root of 4 squared plus negative 3 squared. That's 16 plus 9. Square root of 25 is 5. So, it's going to be 1/5 times vector v. 1/5 is a scalar. It's going to be 4/5 I minus 3/5 j. That's our unit vector. I did it a much harder way. Oh, I double checked. I checked it. Is this really a unit vector? Does this really have a magnitude of 1? So I went ahead and checked it on my building notes. I took 4/5 squared plus 3/5 squared and took the square root of that and showed that that was 1. Okay. But that's the unit vector. All right, here's another important thing. Any questions on this last one? Okay. A vector can be expressed in terms of its magnitude and direction as, so vector v will be equal to the magnitude of v times the cosine of the angle between it and the x-axis plus the magnitude of v times sine of j. And now, so this is why we needed to know trig to do vectors. We're going to use, guess what? The x component is going to have a cosine, the y component is going to have a sine in it. Okay? So we're going to use this. This is also important. Okay? The jet stream is blowing at 60 miles an hour in the direction of, we got north 45 east. So this is, it should be right there. Okay, this is 45 degrees. This is 45. And this is magnitude of 60. So the magnitude of vector v is 60 in the direction, our theta is going to be, in terms of the standard, is against the x-axis. Our theta happens to be 45 here. And at 45 degrees, cosine of theta is the square root of 2 over 2, and sine theta, same thing. So now we're going to do this. V equals, the magnitude is 60 times the cosine, square root of 2 over 2, I, plus 60 times the sine, J. We're going to simplify that, get an exact answer. To get the exact answer, it is, we want exact answers whenever possible. Use your unit circle. Does that make sense? So we've got, if you are given the magnitude of a vector and its direction, the direct x-axis, standard position angle, then you can find the cosine and sine on your unit circle. Or if it's not a 30 degree or 45 degree, then you can use your calculator and approximate it. And you can rewrite the vector in terms of its magnitude and direction. It can be written. So you can go that way. All right, I have a Kahoot. Do you want to do a Kahoot? All right, Kahoot. Okay, so this is polar coordinates of place. Just pick nicknames, classic. I don't want real names up here. Just pick a nickname. Anything you want, food, cartoon character, Rafiki, whatever. Okay. Stacy. We got everybody? 15. All right, we got Mel Gibson. Get everybody now? I think so. Okay. Start. Is that true or false? In the polar coordinate system, each point is unique. True or false?
Why is it false?
Why is it false? Because you can rewrite a point in all those different ways. You can add 2 pi, you can make r negative and add multiples of pi or subtract pi's.
Oh, God. Threw me off with a snowflake.
The snowflake. Okay, I added fun little pictures, but it's nothing to do with problems. Okay. All right. All right, Alice is in front. Convert 2 pi over 3 from polar to Cartesian. You can use your calculator.
It's this music.
You want me to turn it down?
No, it's fine. I'm just saying, I've never heard this ever played. Abel.